is sustainable in nature. And let me just give you the agenda of today's talk. What is sustainable technology in Indian context? What are the challenges and what's related to the VLSI lab and microelectronics and MEMS lab? That is mostly the sensors, actuators developed from this lab, and also VLSI chips, which sensors I will talk about. And all this work actually carried out in the lab at IIT KGP, which I will show during the next 1.5 hours. So I will just quickly give you that what is the meaning of the sustainable development. The use of renewable and non-renewable resources in a manner that satisfies our current needs, but does not compromise the future availability of resources. So you understand every lines of that. We are all fighting for the resources, which is very scarce, even water. So the clean drinkable water is also becoming scarce day by day. Even the pure oxygen, we cannot breathe because of these contaminations of various toxic gases, etc. So that involves something like we need some kind of a development in the domain of control the water safe to drink safe water, as well as to breathe safe air. So you know that technology in sensor is going into that directions. So I will focus some of that. And according to United Nations, the sustainable development meets the need of the present without sacrificing the ability of future generations to meet their own needs. So you know your future our country now 135 billion, 35 crore people, 1.35 billion. It will be 1.5 in the next 30 years. So that future generation should also have the same or better life which they are expecting from us. Therefore, they should have their ability to generate their needs. And if you look at the elements of sustainable developments, first of all, there should not be any poverty and zero hunger, and the good health that is chartered by United Nations. Good health and well-being. So think of it that along with the air and water quality monitoring, also the health monitoring, and therefore sensors in that domain are becoming very, very dominating at this moment. Affordable and clean energy. So in energy also, we are actually going for renewable energy as well as energy harvesting approach. Decent work and economic, not at the cost of others. You know, industry innovations and infrastructures. So industry in India, their innovations, the R&D wing, especially in collaborations with academia, should be much more stronger. It is not very strong at this moment. But if you look at the advanced country, developed country, there is a very strong academia industry collaborations. Then, you know, climate actions, all of you know that with the green world and the carbon footprint and so on. And also you have to take care of the life below the water. As you know that recently it came to the news that how the leakage of diesel actually perturbed the total life under the sea. So think of it, this is also quite vulnerable. And also on the land, our creatures, the birds, trees, and the nature. So we have to take care to get a sustainable development. Okay, so if you look at the sensors, so-called whatever way we were manifesting, these are actually the main domains and where you find their applications. Okay, nothing outside that scope. Basically, we are looking for a sustainable development and to give our solutions cost effectively to the people, the common mass. And that's the idea of IoT. So if you look at the framework of IoT or smarter planet, actually the key elements of that would be all of them or any one of them. Then sustainable development aims to develop an inclusive growth, elevating the poorest population towards better living conditions. India is at the crossroads of opportunities and challenge in the pursuit of sustainable development. We are hoping to get $5 trillion economy within next 3 years. So this is the biggest challenge given to us, along with the challenge of Atmanirbhar Bharat. So to make our own, to solve our own problems. It is among the largest economics and promises to experience high economic growth. But at the same time, a large section of the population doesn't have access to bare minimum of the benefits of economic development. So we need that kind of a horizontal growth, not a vertical growth. So the advantage of science and technology should reach common people. So we have to think of, especially for the healthcare and pollution measurement and so of this, it should actually go across the common mass in our country, even to the world. So if you look at these main challenges, poverty, defeating the preventable diseases. So there are sensors and all these areas where, and even all of you know that today's pandemic, that vaccine and how to actually inject the vaccine, all these things are becoming the cold chain and how much drug is required. So all these things will come up when this vaccine will come in the beginning of this next year. Mastering the energy economy and providing the energy to our economic needs without wrecking the climate and our environment needs. So that is also very, very important, that we should not disturb our nature where we are actually developing these solutions for the mankind. So I will throw upon some of the ideas. So my talk following talks will actually focuses on those kind of developments happening in my group. Adapting to the degree of climate change that no longer be avoided. So you need key approach for the technology sustainable development need assessment. You have to know what is the requirement of our country. Then you develop the technology. Technology appropriations and adoptions to the social engineering. Capacity building, technology empowerment, sustainable. Because you can make handheld medical devices for detection of the vital statistics of living being, but if you require a very sophisticated technique which requires training, then how can you reach to the mass people? So you have to give a solution which is acceptable, even without training or any people with little bit of knowledge can help. Otherwise, it will be difficult to reach with 130 crore people at the nook and corner of our country. So there should be some kind of a social engineering, adaptation of technology. We should not look into always the westernized solutions. We should have our own solutions. We should make our own approach in thinking or rethinking. So that is, I would say in a nutshell, what is going on in my group. The essential objective is technological sustainable development. The LSI trends, the healthcare, the energy and the water, as well as water and air. So all are quite important in this domain. So around that, we try to develop the sensor technology or the corresponding VLSI circuits so that we can have a sustainable growth and our country-specific developments. So if you look at this one, what kind of policy the government is coming up, I will spend 4 or 5 minutes on it, because you are all faculty members, you should be knowing about the approach what government is thinking at the moment, how actually evolved. And when you look at the semiconductor industry, that it is not only VLSI circuits, also the miniaturized sensors. Both are equally important, and their integration is more important. Therefore, as you know, India does have a fantastic workforce. IT, we have done the revolution throughout the world. We are the IT leader. But can we have the similar kind of skill set where we can actually have the design house of the world in VLSI and the sensor technology? Because we don't have any good foundry. Our foundry, we have three foundry. One is actually under Department of Space at Chandigarh in SCL, which is 180 nanometer support you can provide, but that to a very limited scale. Then there are 1 or 2 DRDO's lab, Defense Research Development Organization. But also that is, the scope for that is also limited. So we don't have a full-fledged foundry like to go to 65 or 42 nanometer technology. And even a small country like Taiwan does have that. So they are the world 90% chips, whatever you are finding on your gadgets, you will find the chips coming out from that small country having a population of 2.38 crores. So you think of it, 135 crore people in India, we don't have the foundry, but 90% of the chips that is coming out from Taiwan, which is actually having inhabitants is 2.38 crores people. So 60 times roughly. So, but we can't, because as you know that the foundry and the technology, they have much ahead. Even all of you know that even Intel, biggest among the VLSI semiconductor industry, Intel and Samsung, they're the top 1 and 2. Sometimes they swap. But Intel have stopped their productions in 5 nanometer node, and whereas the TSMC, the Taiwanese company, is not only successfully at 3 nanometer, but they are actually is planning in 2023 of 2 nanometer technology. So it is not that how big is your country, but you need the GIL. Okay? You need the GIL, and all the development of this Taiwan semiconductor comes around 1987. 1987 is the starting point. And our CD Pilani actually established much before that. So that is the Sri Pilani Central Electronic Engineering Research Institutes under CSIR. So even we have developed the initiative even much before that Taiwan has made. But where they are now and where we are. So that question should come. But if you look at the overall scenario of the business model, how it has been involved, one is called the integrated device manufacturing, IDM model. That is, all these companies like IBM, Intel, in say early 60s or 70s or 80s, they used to do everything: marketing, sales, design, IP systems, manufacturing. So it is as a whole is a company. Solution giving to all domains and integrating them, so they are the providers of everything. But later stage, after say 1987, or I say that starting point of Taiwanese semiconductor development, then there is a fab-lite model. In the fab-lite model, actually, the industry houses, they try to spin off, or they try to outsource the manufacturing, partial manufacturing, to the foundry partners. So that is the genesis of the TSMC, UMC, and all this foundry contract. They are not making their own chip. They are actually giving service. Just like a kitchen, right? You give the spices, and the recipe, they will make that product. So like that, they are actually the manufacturing of those chips, these fab lights. So as far as the business model is concerned, those companies like Motorola, Infineon, even now Qualcomm and all, I will come to that, their business model is like that. So marketing, sales, design, manufacturing, and partial manufacturing outsourcing by information. But now, what is happening after 2000? This model comes from fab light to fabless. First with fab, then fab light, partial, and then completely fabless. Most of the companies, you know, that like Qualcomm, Broadcom, even TI will be fabless in the coming years, and they will only take care of this marketing, sales, and the design IP, right? And then the foundry partner will be across the world, like Global Foundry or TSMC or UMC, United Microelectronics in Taiwan, and so on. So that is the fabless concepts, okay? And there I find the scope for Indians. We can generate billions of dollars of IP in that design IP. So if you look at the today's scenario, almost all the companies, top 10 semiconductor company, I start from India, Samsung, then your SK Hynix, then all the semiconductor company like Qualcomm, Micron, they are the leader in memory devices. All of them are setting up their R&D center in IIT, in India. Why? Because they know that we have the potential of creating that IP. And that, you know, that only in the Bangalore, there are 67,000 MSMEs. And there are, I think, 2-3 years back, there are only 200 fabless startup there. So think of it, the ecosystem has started to build up. And when I say that the fabless concepts, that also includes the devices, sensors, as well as the circuits. Now the whole approach give a complete solutions. Don't show me only one component and circuits, but give a complete solutions needed for IoT applications or smarter planets. So that is the scenario, right? So I think that all the faculties and the listener are getting some sort of an idea that where we are standing at the moment, and so that will give you an idea that what kind of problem they should find out for our country, and which will be more sustainable, and maybe for the students to get benefited out of that. So now fabless model is wafer supply. If you look at the device design, process technology, high voltage testing know-how, or any testing know-how, product qualification know-how, these are your demand where you can actually contribute, okay? Then application, product definitions, design support, custom relations, that will be the industry. So there will be assembly house, there will be packaging partners, silicon foundry and wafer supplier. They're all actually different entities, but they're integrated in synchronous with all these activities, and finally it goes to the customers, the common people. So the whole scenario now has changed from the integrated device manufacturing concepts of 70s and 80s, early 80s, now coming to this fabless manufacturing in 2020. So I just why I'm so interested to talk about it, because India has got specific plan how to develop that one, and I will give you to this, and where are the opportunities for both the small scales, medium scale industry and academia. So we have to break the we have to think beyond the Moore's law. So if you look at that, I have already mentioned about that, how the development from fab light to the fabless. Now if you look at Indian scenario, total semiconductor industry in 2015 was $14.5 billion, and now in 2020 it is $52.58 billion. So if you look at the cumulative accumulated growth, it is nearly 30%. think of the opportunity. And the world semiconductor market is $485 billion. Even for there is a small slip from that because of the pandemic situations, but people are saying that next year onward, it will also getting a huge boost because of the 5G technology, because of this the cloud computing, AI-based techniques, and automobile applications, and the virtual platform development. So there will be huge demand in the semiconductor industry. So we'll get a huge boost after in the year 2021 in the from the second quarter. So that is the predictions of today's semiconductor industry. Okay, all are suffering because of the pandemic and various business problems, deals with China and all. But in India, you think of it, that there is a market today is $52.58 billion. So think of it, what will happen after 10 years. So don't you think you have a scope to contribute in it? I hope every Indians have the scope to contribute in these developments, where the growth is 30%. So there is no way to slip this opportunity. We should not miss that bus and contribute and make, as you know, that our electronic import more than the oil import very soon. So think of it, how much foreign money is being spent, losing our foreign money because of electronic import. So if you can develop our own solutions and own developments, and that I say that now you may not have a process or may not have the fabrication support, why not you work with, take the synergy of the semiconductor fab and also take the advantage of the leadership in design of sensors and VLSI, work together and make and prosper. So that's the whole idea of today's vision. So there is a national vision to that. So how the MSME and the idea is that enable a tenfold growth in the Indian fabless design. So whatever we have, and commercial design incubator, center of excellence, appropriate libraries of EDA and IP tools. So that is to boost the ecosystems of the Indian fabless manufacturing. So idea is that, one second. Hello? So I'm actually in a class, so can you talk to me at the same time? After 1.5 hours. So if you look at the things that we should have at least 10 fabless MSME within at least the turnover of $50 million. So now you know that it is not only the job opportunity, but also opportunity for your own entrepreneurship, own startup. So this government is very much actually conducive to this kind of ecosystems. And what is the requirements in India? The opportunity and seed funding, market assurance, people skill, EDA tools and MSMEs, CPU IP, processor, you know that we have made our own CPU, the processor Shakti, and now there is a call that how can I use that Shakti for some application developments, assembly tests, evaluation of rapid prototyping and EDA tool startups. That is a very important constraints today, that EDA tools, that is your Cadence platform or Synopsys platform for device design, as well as the Coventerware or COMSOL for sensor developments or miniaturized sensors like MEMS, microfluidics. And therefore the availability of the tool should be available at a cost, reasonable cost, so that the academia and the industry both get the benefit out of it. So look at that Indian policy. Is the first one is called incubating. The virtual tool cloud, the thinking of that all the CAD tools will now be available in the cloud. So with a minimum registration fee is you can get the license and you can actually start the design, both in sensors and also in the VLSI. Then you will get some R&D grant from various organizations like DST, MIT, and other DBT and others. So this is more or less the where the qualification threshold or the stringency is much less. But after that, gradually it increases because you have to convince once you get some kind of a technology readiness level of say 5 or 6, then you can approach your venture fund to product phase support. So it is called productization. Okay. That you can get soft loans from the operation scale up from few hundred to few lakhs, millions, and then market interventions. So that this is the vertical actually. So if you look at the y-axis, so that is the incubations and that is to accelerate. And if you look at the qualification threshold, it will be more and more as we reach to the top of the pyramid, as usual for any systems. Okay, so that is the kind of policy we are thinking of to India for fabulous manufacturing and also to help India. And I am actually coordinator of this fabulous manufacturing activities with India and Taiwan. And I will not go into that. Yeah. So I'll just say things. So let me start my activities. We have this is at one point of time, maybe 2-3 years before. I have that group that many students have gone, and many students have new students has come up. So you will find that it is Vice Chancellor of National University of Singapore, and some of them are already left. He is in now IIT Goa, and she is from Jamshedpur, working on the microneedle part. He is faculty member of a central university, and those people are still with me, and more people are working. So nearly 15, 16 students, PhD students working with me at different domains. And this is a bird's eye view of the lab. I will give you a virtual tour of what kind of facilities we require for fabrication of sensors, and which will give you the insight in the virtual tool. So these are the still photography, but I will give you a virtual tool for that. So just wait for this. I would say that it starts from mask making to this is the DRI, this is the mask aligners, where I am actually fabricating the stuff. This is the laser Doppler orgometer as well as the probe stations. These are probe stations where wafer you can actually probe, and this is the diffusion furnace for doping of the silicons, and this is the stylus measurements for. So I have many more equipments, but I'm showing some of them. In the virtual tour, I will give you the glimpses of what we have in this lab. Now, I will go into this. If you look at that, this color, the sustainable space applications, and there are several activities going on, but I will focus on those features colored in this purple. So this is the sustainable space application for MEMS-based satellites, which are supported by ISR, microfluidic platform for single cell culture, that is for healthcare applications, capacitive type immunosensors arrays, nanowire embedded MEMS thruster for self applications, that is carved over here, the 2-terminal nanobiosensors. I have a much larger group in inertial sensors, like accelerometer and so on. I am purposely avoiding those because I have chosen those topics which can be done in India in a much lower cost, that any one of you can actually get an idea, and then you can actually make this without investing a lot. So that is why I have chosen few areas where you can get the idea, and then you actually get the problem statement and give the solutions to our country. So I will first start with the sensors and actuators and how the nanotechnology is being utilized for space applications and also for sustainable developments. So all of you know that the satellites that is launched via PSLV or GSLV, they are actually the payload. The total weightage is more than 100 kg or 1000 kg. So they are very big satellites. And even if you reduce 1 kg weight, then it will cost $10,000 straightway cost reduction would be there. So people are thinking that why we can go for a smaller satellite. So people thinking of satellites below 10 kg. So that becomes your satellite, nano satellite. So there is a concept called satellites in that 1000 kg scale, and below 20 kg we call it micro satellites and the nano satellites. So many of you can remember that India can boast of launching 114 nano satellites in the space in one go. That in one go I can actually put 114 satellites at one time. And these satellites having weight less than 10 kg and having all the functionalities, most of the functionalities of a big satellites. So I can make a satellite colony or clusters, and we can solve very problems like the darshan or any beamcasting, telecasting, or remote sensing for weather predictions or for harvest mapping and various population demography. We can make use of that satellites, where in spite of one, you have hundreds, and make use of that miniaturizations. I always say that the miniaturization and integration is the key word for all of us working in the domain of VLSI and sensors, because it is sustainable in nature. But it is not going to give you any solution to do it in civil engineering and construction engineering. You cannot have the functionality of that. So you have to choose which one you want to miniaturize and integrate. So if you look at here, you know that in space, I am giving us first the problems. So all of you know that in space, the acceleration, we say zero gravity conditions. So all this movie and the international space stations, you find that the astronauts, cosmonauts, and the space explorers, they're actually floating because there is no gravity. But if you look at carefully about this in their studies available in Google from international space stations, there is actually some gravitational field, and that gravity is order of 10 to the power minus 6 to 10 to the power minus 9 G. And that is the kind of acceleration there. You cannot call it zero, but there is some gravity which is 10 to the power 1 millionth of the gravity available in the Earth. And then you know that this gravity is cannot be actually measured in the common in Earth, whatever common strategy we have. Whatever common strategy means, either you go for piezoresistive kind of accelerometers or piezoelectric kind of accelerometer or capacitive accelerometers. Those transducers or in sensors are basically, you know, they are linear in nature. So you need an appreciable displacement of your proof mass to get an appreciable signals, either voltage or current, which will define the accelerations. In space, you think of it, you have a 10 kg satellite, so 10 to the power 3 gram or 10 to the power 3, and there is the gravity is 10 to the power minus 6. So there will be actually millinewton force. Okay, so that force is not enough to give you a sufficient inertial force to make any kind of movement of your inertial mass so that you can have the corresponding current change or voltage change. So you cannot actually, all the sensors that is being utilized in space will be something different. You have to think of a very new ideas, new concepts into it. So this is the idea that how you can make a sensors which can detect the gravity in space order of -6. So in spite of the conventional one, then we have chosen a new approach called quantum tunneling sensors, electron tunneling sensors. So you know that all of you know about in device the tunneling phenomena. So how this tunneling phenomena in between the tip and the counter pad can be utilized for measuring the acceleration in space. And why it is so important, because I will come into the next points. If you look at the satellites, so this is the basically the picosatellite or nanosatellites. You know that there are all the accessories are within that, and solar panels you can see. And there are, when they are actually launched in a particular orbit, after that, in 10⁻⁶ acceleration, if there is a drift, then what will happen? The satellite would have actually moved. It will drift away, and so that the transponder which is beaming India would beam actually the Arabic Oceans or Arabian Sea or Pacific. So you have to control the drift. There should not be any drift. So idea is that whenever they will see some kind of a drift because of the acceleration, that too in the micro g level, there should be some kind of a thruster which will give an opposing force to actually to oppose the drift, so that the satellite will remain in this orbit in stable conditions, so that always it will beam India, not other country or the sea or oceans. So look at it that because of the Newton's third law, if you can thrusters in one direction, other direction, there will be a opposing force. That way you can actually stop the movement of the device. So counter force. So even the drift of micro g, you can actually control. There will be a command. Once you say the micro g, what I say tunneling accelerometers will give the signal to the earth, and earth will actually turn on a thrusters, and the thruster will be on, and that will give you a sufficient thrust and will actually give you the opposing force, so that satellite didn't move away. So that is called attitude control. So I will actually, the whole systems what have been developed in my lab, I will show. This is actually sponsored by ISRO. So we call it as a MEM space satellites. So if you look at this tunneling, there is a current. So obviously you need, after current you need a voltage. So you need a transimpedance amplifier, TIA. And the kind of transformation I require is from the nanoampere to millivolt. So 10⁻⁹ to 10⁻⁻3. So you need 6 order of magnitude gain. Okay, and that gain, transimpedance amplifier gain, means roughly 120 dB. So you need an amplifier for that is 120 dB. And all of you know that this kind of acceleration sensing always done in a closed loop form, not in an open loop form. In open loop, you can get the signal in your oscilloscopes to find out that whether the accelerometer is working or not. But actually, I will show you that there will be some sort of a counter force, so that it will remain at constant gap, and that will introduce a constant current. So it will work in a constant current or gap mode. And the amount of voltage required to set that point is known as the measure of the accelerations. I will go into that. Then there will be something like the signals, that same signal is coming to a scaling voltage. So this is the inner loop and this is the outer loop. And here there is a reference voltage. I know the reference voltage where it is stabilized. And then there will be an actuation pad. This will actuate a thruster. The thruster will provide you, what is that actuator part? It will actually turn on the valve. I will show you the valve, how to design it. And the valve will trigger, and this propellant, for example, hydrogen or even vapor, water can go and vaporize and give the thrust. So it will automatically, the onboard measurements will be carried out, and we can see that the drift has been arrested. So I will make, again, this is very clear that you need a completely new avenues of solving this problem, okay, not any conventional one. Okay, so you require some new ideas of tunneling phenomena coming directly from the quantum tunneling effects. And also you need a high gain transimpedance amplifier. You need the concepts of constant gap mode or current mode approach, for which you need a feedback control. And the outer feedback control, there will be some kind of a actuators which will actuate when there is a drift to a micro valve, which will open, and the propellant will go to the thrusters, and the thruster will evaporate that propellant, and it will emerge out of the and give you enough thrust so that the drift of the satellite is arrested. So this is the whole actually the systems where sensors and actuators, in nice examples of sensor and actuators together. And look at here, the whole thing should not weigh more than 10 grams. Okay, the tunneling accelerometer weight is 10 milligram, and the whole chip and everything would be few grams. So within 10 grams, you can actually make the whole things, including the thrusters. So think of the payload. So the whole idea that 10 kg satellites, pico satellites, how to actually make a corresponding sensors and actuators, because if you make a, you know that what is the accelerometer now used for acceleration? This is 25 kg. So that 25 kg, that accelerometer is only the weight of that. And think of it that if your whole satellite weight is less than 10 kg, so you need solutions. You need a new kind of thinking process. Okay, so we completely developed that one. How the new concepts has come. So idea is that suppose you have a silicon, and this is a surface micromachining process. So you have the silicon nitride and polysilicon layer, where you have patterned the polysilicon layer to define the electrodes, and you have this another oxide layer which will actually isolate the top polysilicon layer and the bottom polysilicon layer. The bottom polysilicon layer defines the electrodes. So you can finding carefully that there are three electrodes. One is called the actuating pad, and other one is a tunneling pad, and this is the test pad and all. And this is something like a cantilever beam. And if you have a good eye, you can see that at that point there is a small tip, and that tip is the tunneling tip. So now think of it, because of even micro g acceleration, it will actually give a movement, and then when the gap between the tip and the pad is ordered of few nanometer, just think of it, say 10 angstrom or 1 nanometer, then actually we will find a current that is called the tunneling current. I will explain what is tunneling current. And then if there is a displacement of the cantilever beam along with the tip because of the accelerations, then definitely there will be change in the gap between the tip and the pad, which corresponding to a change in the current. And that change in the current is exponential in nature. There is the actual figure and picture of the tunneling sensor, and this is the actual curve, you can find it. So what is that? This is the beam what I am trying to mention, and this is the tunneling pad. You can always say that And this is the chip level developed at IIT Kharagpur. This is for gyro. I am not going into the gyro that will actually sense the rotations and tilt. So I am just concentrating on this part. So you understand that the gap between this tip and the pad is around few micron, because the thickness or the length of the gap, length of the tip is around 0.73 micron. And the gap between this is 2 micron. So there is a gap of 1.23 micron. So, but I require a gap between the tip and the pad is 1 nanometer, 10 angstrom. How can I do that? Then I explain you the facts that actually I will give a voltage over here, and that voltage will electrostatically or capacitively actuate the beam. So the beam will pull down, and along with the tip, so tip will also be pulled down, and then the gap between the tip and the pad will be reduced. Clear? So it is like biasing a transistor. So I will bias the whole systems with certain voltage. So you can look at the curve, actual curve. So I am giving the voltage 1 volt, 2 volt, then 3 volt. There is no current because the gap is more. So tunneling probability is less. But when it is more than 4 or 4.7, around 5, okay, this is 6, this is 2. So then actually it is the onset of the tunneling. And you find that when there is single tip, the tunneling current is very, very less, roughly 1.2 nanoampere. It is 0 to 5 nanoampere, this is the scale, 1.2 nanoampere. But in spite of a single tip, when once you have 100 such tips in one beam, then you can raise the temperature, the current to around 40 nanoampere. So you can find an exponential rise, a small change in the voltage that is corresponding to the change in the gap because of the actuation. You are finding a huge change in the current. So what we have done, that we have fixed that voltage at the onset of the tunneling current, and then what is happening, if there is a displacement of this tip because of the acceleration at -6, 10 to the power -6, or 10 to the power minus less than that, then displacement will reduce the gap in angstrom order, and thus it is so sensitive that I can actually see the corresponding change in the current. And from the current, by applying a transimpedance amplifier, I will transform with a 100 to 120 dB gain. I can actually measure the voltage, but it is open loop. But I want to measure in closed loop, so there will be another voltage which will add this voltage or subtract the voltage, so that it will remain in the same current or the gap. So the amount of voltage error or to be added or subtracted is the measure of accelerations. So that is the way how you can actually measure the acceleration in outer space. Okay, but as you know, this normal accelerometer for a measure for the car, all your airbags are actually made of actually actuated by an accelerometer, and which accelerometer is basically piezoresistive or capacitive one, where you require micron level displacements, but here it is angstrom level displacements. That is enough for giving you the actuations. So this is, I already mentioned that how actually make this structure sensors, and there will be 6 such sensors in plus X minus X, plus Y minus Y, and plus Z minus Z. So orthogonally you can get the acceleration in 6 axes, and then you transmit that signal to the control command to the earth station, and there will be a trigger to the microvalve. The microvalve will be on, and the propellant will go inside, and it will be activated. So if you look at the inner view of that, there is the camera, the torque coils, the camera, battery enclosures, reed gyros. I'm not going into the gyro side. I'm only talking about the accelerometers, which is there for measurement of accelerations. The electronic enclosures, and this enclosure requires because the temperature there is minus 40 degrees centigrades, and there the vibrations, there is radiations too, so you have to make this device radiation hardened, so there should not be any drift in the threshold voltage because of the radiations and so on. And now look at the microthruster. There will be 6 microthrusters in all directions. So according to the acceleration sensing, the microthruster will thrust on to oppose this kind of drift due to that accelerations. So now look at the thrusters. How to make a miniaturized thrusters? So if you look at the structures, it is silicon. We have micro, and this is the red part is called the hot plate, or it is the heater coil, and so both the side we have the heater coil to get the redundancy in the space. If one fail, then another will work, and this will heat it up. Okay, so the hot plate will be heated up, and then the liquid, the propellant coming vertically from that port. Okay, and they are actually being heated up. So there is a phase transformations. What is the phase transformations? From the liquid phase to the vapor phase, and we have made the area and the flow of the liquid in such a way that it will not, there will be no residual liquid phase, so that it will, so that all the vapors are actually coming from that nozzle. You know, this is a converging and diverging kind of a nozzle. Here, the vapor will actually come out at a huge speed, at least Mach 3, that is 3 times the velocity of the sound, and that will go outside, and that will introduce the kind of, from the exit nozzle, that will introduce the kind of a thrust, and that thrust is, they have given me a very important specifications from 200 micronewton to 1 millinewton. And just to look at it in space, 1 millinewton force is good enough force for the satellite to be launched or to be kept in the same orbit. Now you know that there is some issues to be involved, because outer space, this is the black zone, is the space where the temperature is minus 20 below that temperature. So suppose here I am using VLM, simple water. So water gets heated, and that heated water at 100 degrees centigrades, if then actually it converges and diverges and then passes through that nozzle, immediately it will be moisturized, and it will form the ice crystals, and that will clog my exit. So how to avoid that one? Actually, you have to make super saturated steam at 120 degrees centigrade. So you raise the temperature of the vapor to 120, so that this kind of the freezing of the liquid or the moisture would not occur, or the vapor would not occur. There should not be any accident into this. So you need a temperature bath here, which will give you temperature at least of 120 degrees centigrade. Now there is a concept called specific impulse. That is in 50. The impulse means the thrust. Actually, you can quantify the thrust. Okay, one is this thrust in terms of Newton. Other one is a property of the propellant. For example, the water, they have a property of 50 seconds, whereas the hydrogen N2H2 does have 150 impulse. So that will give you much bigger thrusts. Okay, so depending upon, because as you know that when we develop this one in the lab, then we cannot actually go for hydrogen, because hydrogen is not an applicant for civil lab. It has to be tested. So this has gone to the space, and they have tested it with hydrogen. Okay, so that is the idea of how to make a sensor, how to make a actuator. I have not yet finished, and to give an integrated solution. One example is like space applications. So if you look at there, physically, what do you mean by that? So that is the VLM. So you know that this, we are making a flow very slowly. So if you have a close eye, you can see that a droplets of water going through that nozzle, the hot plate, and the vapor is coming out, and the vapor is thrusted so big that it is able to even to move that the copper plate. Think of it, that there is even a small droplet that is again evaporated is being able to give enough thrust so that it moves. So that gives the idea, right? To understand that I want to introduce some kind of a 200 micronewton to 1 millinewton of force or thrust, and that will be created, that will be controlled by the temperatures as well as by the nozzle size, the aperture and the angle, nozzle angle, and as well as the flow rate. So if I increase accordingly, the thrust will change. Clear? So that is how I demonstrate that how a miniaturized thrusters, okay, can be developed, and this weight cannot be more than few grams. And also the accelerometers is, I said, that is few milligrams. But then I talk about the sustainability. You know that then ISRO given me a challenge that, okay, you develop that one, it's working fine. But to develop the heater, you need to give a current, and that consumes per shot 3.6 milliwatts of power. And all of you know that in a satellite, the lifetime is 5 years, but actually we design it for 10 years. And when the solar panel is folded, then we get actually 40 volt. And when it is unfolded or not within the sun, then the kind of voltage is 28 volt. So all the system in the rack should be able to work at 28 volt as well as 42 volt. Now, next question is the survivability. So amount of propellant that will be there, I want to miniaturize the dimensions of the satellite. Okay, so it is MEMS satellites. And now if the amount of liquid, the propellant, would be also less. So, and also the power requirements, if it is 3.2 milliwatts per thrust, so my lifetime of the satellite will be less. Then they given me a challenge that can you really make something, reduce the power consumptions? That is the question of sustainability of it. Then we actually thought of, can we get rid of, but still we want to produce the temperature of 120 degrees centigrades. So here you need the breakthrough. So what is that idea, out of box thinking? Then we thought of that in spite of water, the one thing you will come, one more oxygen is H2O2, right? H2O and H2O2. H2O2, hydrogen peroxide, is very unstable. And then if H2O2 is passes through, it actually, when it breaks to H2O and oxygen, then actually introduce heat, and that is the exothermic reactions. Now, that gives us, that clicks in our mind, that in spite of water, if we can make H2O2, and then we can actually lower the cost of the propellant 50%, because the impulsive is much higher for H2O2. But we need some kind of a technique to enhance this temperature, that is this more rigorous chemical reactions. How and what do you think of it? If you want to make a forward direction accelerated chemical reaction, you need a catalyst. So we just make manganese dioxide, MnO2 nanowires, where the nanotechnology is coming into the play, is actually the answers. So what we have done, that in spite of that heater, replaced with MnO2 nanowires, okay, tested on the hot plate. Hot plate is now free from the hot, this kind of wares for tungsten filaments for making the heat. So now think of it, the bed is now actually embedded with MnO2 nanowire. And MnO2, just like as a, it doesn't actually, a catalyst means with the reactions it remains unchanged, but it helps in the forward direction reactions or reverse direction. In this case, we require the forward. How much rigorously the H2O2 breaks into water and oxygen. That will give more thermal energy because exothermic in nature. So that exothermic nature will introduce huge temperature, and water means water, the H2O that is coming out from H2O itself will immediately gets vaporized, and that vaporized water is now passes through the nozzle, and that introduces the kind of a thrust, and this kind of a thrust you can see that how with the thrust we are getting from 200 millinewton to 1.2, 200 micronewton to 1.2 millinewton of thrust without requirement any power, any battery. Think of it that by this way, I have increased the lifetime of the satellite, right? Because every thrust you require to consume a 3.6 milliwatts of power, but in this case, you do not need any battery power. So it's a sustainable one. And this approach is known as the energy harvesting technique. It is nothing but we made a cavity, a reaction cavity, in which we have introduced a very unstable liquid H2O2, and with the catalyst, we increase the thrusts by exothermic, by vaporizing the water, and finally given that one. So if you look at this approach, I am not going into the fabrication steps. So this is the same nozzle, okay? This is the same nozzle with this input. We are giving H2O2. H2O2 is fed into it, and then it is actually passing through that converting angle, and the water passes, and this the kind of flow rate is around 2.5 to 30 microliters, and then finally goes out of that, and it gives you the enough thrust. So now you can think of it that when you try to solve a problem holistically, then you have to usher completely new ideas into your thinking process. For tunneling accelerometers, we have introduced the quantum tunneling phenomenon. Whereas in this case, we have used that energy harvesting approach to reduce the lifetime, to increase the lifetime of the satellite. So I want minimum 10 years of lifetime of a satellite, which is supposed to be for 5 years in the orbit. Okay. But actually, the space grade applications, you need to make it for 10 years. Every budget counts, every power budget, every grams of weight counts there. So now coming into the actuator, after the command, that is the accelerometer gives you the accelerations, and then you give you the instructions to the valve. So valve will be open. Normally the valve is closed now, and when it is actuated, then it is actually, if you look at here, then actually this valve is open, and the propellant here at H2O2 is coming out, and then it is going down with this diverging points, and this is the path route comes. So after that, and there is a strict things that they want the propellant to go to the thrusters at 1 bar pressure. And then this is the concepts that this is the, if you look at the silicon, this is the color is, this is the silicon, and here is the piezoelectric disc, and the supporting mass, and this boss tip, this is called boss tip. So bottom wafer, piezo actuators, the end plate. So when we give the voltage, then actually it moves up, and when it moves up, then it opens up, and the liquid, they have propellant H2O2 in this case, or nitrogen, whatever, will actually go, and then it will go to the thrusters and evaporate it, and will give the corresponding thrust. So that is the whole story. So initially it is closed, but when it gets a command, actuation voltage will or make it open. So now the liquid will be available to the thrusters, and thrusters through MnO2 nanowires embedded hot plate, it will create the thermic energies, and that will break the water, and that water will be evaporated and pass through these nozzles and introduce a kind of a thrust to arrest the motion of the satellites. So this is the cross-section view, the boss tip and the inlet and the outlet. And this is the, I need a lot of other things like sealing the ring, and also there's leakage and so that. And that is the most important point, right? Idea is fine, but when you try to make it actually in the lab scale, that too for space grade conditions, then the total challenge is different. You know now what is the challenge ISRO has given me? That okay, I will be using the liquid propellant like hydrogen or hydrogen peroxide, but you have to prove your idea for the lightest gas, helium. And I want 1 bar pressure, but I will give you 5 bar helium pressure. And in that condition, your valve should be closed. Mind it that there should not be any leakage, even at 5 bar helium, the lightest gas. So that is a challenge given to me to think of how to make that structure. These are all miniature structures. This whole thickness may not be 1 millimeter, 1 centimeter into 1 centimeter whole, maybe 0.5 centimeter or 0.5 centimeters. And the dimensions of that holes is few microns, say 200 micron to 35 micron. So it is very miniaturized, very less weight. But I have to prove the concepts not for the hydrogen or H2O2, but more stringently in the case of helium. If it is leak proof, then they will accept it for space applications. So look at here, this is the kind of a jig that has been developed to test it. You know, testing is very, very important. So what is the idea? That there will be 5 bar pressure of helium, and that will go to the micro valve, and then there will be an outlet. It will be connected with a pipe and to. So if there is a liquid or helium gas leakage, then I will see that the helium will actually, drops will come up there. So droplet will be formed. So I have to prove that there is even at 5 bar helium pressure, our microvalve is closed and leak proof, so that there is no helium coming out of that and there is no droplets. So let's see, because seeing is believing. So that has been tested, and once they want to accept something, they will not accept if it is tested in your lab. It will be tested in their classified lab. So that is tested in the INSAT 1C lab. Okay. So that INSAT 1C lab, if you look at here, how this valve is being inserted, this is the piezoelectric actuators. Okay. And they are now very carefully aligning that inlet and outlet. This is the electrical connections, and they through microscope, these are all ISRO guy at Valiamala, at that. Then they make this kind of a jig to test it for space applications. Okay, and now you can see that how the test setup they are making. So this is they are giving 5 bar pressure. So they are actually seeing whether there is a leakage. Now they are actually applying the voltage. Now see that when they apply the voltage, it will start. So now if you apply the voltage, now see 5 bar pressure given, apply the voltage, it starts. So our valve is open, and you can find that the helium gas coming out of that and forming that droplets. But when it is 0, you see there is no 0. There is no. That proves that it is leak proof even at 5 bar helium pressure. Okay, and now we have to, this is my student Vidhan, and now if you look at from the displacement, they are actually finding out the flow rate. So they want to actually change the opening of the boss tip to change the gap between the closer end, so that they can actually control at different voltage the flow rate. So that is also being done. So this is the displacement. From the displacement, the rise of this height, you can find out that this is the rise of the height from the flow rate and all. So this is the way how this has been tested and successful. And after that, it has gone for the productions, and now it is in space. So this is the one such examples I would say that can be utilized, which is self-sustainable. Also, it is miniaturized combination of sensors and actuators. Okay, so let me go to the another sustainable approach. for the health care. So a little bit of um, breathing time I should provide you, that all of you know that at this moment the pandemic situations, people are some people are developing the all over the world. People are developing the vaccine, and for which you need the human trial. But can we make something which will mimic the conditions in a chip, which is called the lab chip concepts, where you can actually test whether your drugs are working on it or not. And secondly, you know that where in a body you have a particular affected cell, suppose the cancerous cells, they are actually surrounded with the normal cell. Then once you put the drug, then drug will affect the normal cell as well as the affected cell. Then how can you actually make a targeted drug delivery? One, and secondly, that how to test it without affecting, without knowing interactions with other cells. Then there is a huge concepts that is all over the world, which is now the current research trend. How to make a cell for testing single from the blood serum, how I can extract a single cell. I can make the DNA testing or whatever after PCR. So I have to isolate the single cell of particular size and shape, which I require to know its influence on the drug in a single platform. So that is where the miniaturized sensors and actuators also playing a great role into it. I am quickly going into this. So this is the microfluidic platform. You can see that. So, and this is the cell. And you can see that how from the mingle of a huge number of cells, actually how we have trapped a single cell on that trap sites. And the rest of the cells are actually gone away with the fluids because they are at a positive pressure. So actually there are two trap points. This is for these trap points are actually temporary trapping or for few seconds. But here, when you actually trapped it in this, it is for longer time. So if you want to do the measurements in longer time, you have to trap it for a longer time. So there are two kind of trapping centers. One is this side and one is this side. Okay. So now I will show you a video where if you have a good eye, then you can find out that how the cells, because of the positive pressure, is being trapped beautifully over those trap centers. And these are all microfabricated structures. And it is not any expensive materials like silicon. It is basically PDMS, a polymer on glass. So I can actually, do a microscopy, I can check the cell and its interaction with this. So when the cell is trapped in a particular positions, then I can introduce the drug and I can find out the reactions of that. Now the whole drug delivery systems, as you know, for the vaccine developments for the COVID, actually they are working on the T cell, the immunology studies. You require this kind of platform, LOC or lab on a chip kind of a platform. So now I am clicking it. So if you have good eye, you can find the event. Okay, it is few milliseconds it will come. So if you look at here very closely, okay, you can see from there, look at that cell first. You can see at any instant we captured the image of the cell. Now this cell was in a temporary trap. How that will come to the permanent for longer time? Please look at it here, and I am clicking it. Then you can see. Sorry. And then you can see. It started to detrapping. Can you see that? Yeah. Now you see that it is trapped. Okay. A single cell is trapped in these fashions. So if I work again, you can see again. See how the cell, this is the cell, is now, yeah, trapped to that. And we can actually manipulate this gap and the dimension so the particular shape cell will be actually trapped there. So that is the platform, which is one of the very upcoming areas, that how to so that we can actually replace the human being for trialing any drug by introducing this kind of a lab on a chip. So all the testing can be carried out. If it is a cancerous cell, then the cancerous cell will be trapped. Then we can introduce the corresponding drug or some other cell to kill it or to make the immunology. Then we can actually see that whole phenomena, whether a cell membrane is penetrated or what is the electrochemical potentials and so on and so on. So that is one of the technology for the healthcare, and how this kind of very interesting approach, just using plastic, a polymer, you can develop that one. This is a very low cost. Next one, again in the approach for making, I don't know how much time I have, maybe up to 2 o'clock I can continue, because I can talk about 6 hours, 8 hours. So, coordinator, can you tell me how long I can?
Yes, sir. That will be okay for us. We can wind up by 2 o'clock.
Okay, fine. Then another very interesting development, I say very low cost. All of you know about the cancer and the prostate cancer. This is primarily for the prostate cancer. So, you know that thousands of patients coming in India, prostate cancer and cervical cancer, these two cancers are very, very huge in number in India. And the doctors, they require some technology that at least to say whether you have prostate cancer or not, yes or no, some kind of a qualitative informations. Once it is say positive, yes, then they will go for the all kind of biopsy and the conventional technique. But you know that just to know a decision whether you have cancer or not, if you can develop something like a very low cost throwaway price, means the one-time device, then you can actually cater to the need of millions of people. And if you look at this curve, I will explain you that there is a strong biomarker for prostate cancer, which is called PSA. Okay, PSA is the K alpha gene code, not doing the biology side of that. And in the blood serum, the existence of the PSA protein, and then if it is less than 4%, you are not in the danger node. But if it is more than 4, you are actually in the early stage. And when it is 10 nanogram beyond, then actually you are in a worse phase. So can you make some kind of a measurement setup or a sensors, semi-qualitative? I don't say it is a pure quantitative measurements, but here the semi-qualitative measurements can provide you the decision making, right? For example, the pregnancy kit available, which is nothing but, you know, it is so simple technology. There is paper, 3 papers are there, and there are gold nanoparticles, okay, on the paper. One is for the reaching of the chemicals, whether the sample has gone, and other for the whether pregnancy or yes or no. yes or no kind of decision. Then actually by microfluidic capillary force action, the sample, the urine that goes through that, percolates through that and actually are tied up with that gold nanoparticles. And once it is tied up with that gold nanoparticles, because of the quantum effects, there is a change in the color. So you are basically doing colorimetry, and that's where if there is no, that biomarker of that sample is not for a biomarker will be appearing in case of pregnancy in the urine. So if that biomarker, it is nothing but it's a gold nanoparticle and the biomarker interaction that introduces some kind of a color change at that point. From the color change, you can say that whether it is a pregnant or non-pregnant. So think of it, I don't have any quantitative decisions with me, but I have a qualitative decisions with me. So yes or no, that is the decisions I can have. So think of it that for a cancer patient, for PSA detections, when we have a marker, the presence of the marker, whether it is less than 4% or 4 nanoG per milliliter, nanogram per milliliter or more than that, that is the vital point we want, the doctor wants. If you give that, okay, at a very throwaway cost, not even 100 rupees, then what the doctor can actually isolate. Otherwise, thousands of patients would have to undergo all kind of standard procedures. Expensive for our country like that. Then how to reach people to the common mass? We should have the kind of sensors which will be less expensive and affordable, like pregnancy kit. So this one is like that. For example, this is on a glass substrate on which you have the gold one, and this is simple SU8 spacer, and on the top another SU8 polymer. And you can see that there is, I just make one floating Petri dish. You know, you do the experiments on a Petri dish. So that miniaturized Petri dish is rectangular in nature, having a depth of say 60 micron and width of say 20 micron. So there is some kind of a pit. And then this, the bottom layer of that is coated with the gold. And I found that you need to functionalize that one. So this is the whole functionalization process, you know, whole functionalization process. So it is called you need the PEG thiol and biotinylated thiol for anchoring, and then correspondingly antigen, as you know, that will be anchored through that. And the biomarker with the corresponding antibody will be loaded that one. And so when they are attached to this, and then, you know, mass will increase. And otherwise, if that there is no such antigen antibody, so you have the lock and the key. So you have made the antigen, okay, this hand, antigen, this is the lock, okay. So that is there sitting on the biotinylated surface on the gold, okay, that is waiting for a complementary antibody. That is the biomarker for your PSA cancer. So that one, when that biomarker is present in the blood sample, so that will be attached to that, okay, and that will increase the mass of that. If that biomarker is not present, then there will be no such attachment, no locking. So it will flow away. So you don't have any change in the mass. But when it is anchored, then there is a change in the mass. And that change in the mass will introduce some kind of deflections of this floating Petri dish, and you can measure the impedance. And from that impedance measurements, you can find out the change in the mass or the frequency. And from there, you can actually calibrate with respect to this. So you can make a semi-qualitative estimations of the presence of PSA, prostate cancer detections, using a plastic, I think, use and throw kind of a lab on a chip sensors, which will give you a very cost-effective and solutions for the for the common mass. So I can actually go on with this. but I have just 5 minutes for you. So I have one options. I will go either to one of the idea that how from the concept you can productize something and then go to the market. So I think I have one visuals for you. I am actually going into that visuals. It is only for 5 minutes. Okay, so please look at it. Then I will again come back. So you just how from the technology from the lab can go to the market. That is a very important thing. So I am just starting that one. So
जब वैसे ही वो अगर इसको नंबर कम दिए हो
नहीं वो किसी हमारे स्टूडेंट का नंबर कम दिए मिला सब यही सचिन का नंबर कितना मिला
so
Sachin Singh, please unmute your mic. Sachin Singh, please mute your mic.
नहीं हम बात किए थे कि चलाए भी नंबर कम नहीं है नहीं कोई बात हुआ नहीं है
so just you wait. Let me.
जाके बहस थोड़ी ना करूंगा कि वो बड़ा ही है आप हमसे तो
Sachin
5
Singh,
बोले
please
तुम्हारा अच्छा
mute
हुआ
your
तुम्हारे को
mic.
कितना भरना है हमके सर आप बता दीजिए कितना कह 91 नंबर भरो
Okay.
क्योंकि
So
कागज मैंने सब बनाए थे
hello.
ओके
So can you just look at? I am just will start this 1 minute. You have to wait. Yeah. Just you have to wait for that. So can you see that? Can you see that?
Yes, sir. Yes, sir.
Can
It
you
is
see?
visible.
Okay.
Yes, sir. It is
Just you look
visible.
at that.
Yes sir visual
So that is how a product developed from my lab is coming. So I am again turning on. Yeah, please. Can you hear the voice?
Sir, the voice is not visible, sir.
Oh, it's not audible. Anyway, so I am explaining. So you can look at it. It is called transdermal drug delivery system. So you know that for any kind of drug delivery, you have to use that either the muscular or hypo kind of a needle. That will be painful, and even for children, it will be. But in spite of that, can we make some kind of a micro needle which will have the dimensions of few microns and which will be painless? So if you look at this conventional needle, it is this one. So this is quite lengthy and its diameter is more than 500 micron. So it is painful. And if you look at the muscular kind of thing, then there is a hypodermic syringe, which is basically less dimensions, but its diameter is 300 to 350 micron. But look at that, what has been developed in our lab is that yeah, you can see that 35 micron inner diameter and 55. These are arrays of needles, which is dimension is 35 micron inner diameter. 100 such needles are made in one go. So you can actually make, now we can show you the complete device. Yeah. So it is, we are calling it is a drug delivery patch. And it is made of glassy carbon. So glassy carbon is so hard, it is 40 times harder than the force required to penetrate the skin. So there is no possibility of any kind of breaking of the of this needles. So you can see from there. Yeah, this is micropump. Yeah. Actually, you can find the text. So voice is text. That is the plan, right? And one thing that Bharat Biotech, they have already announced they have go for transdermal drug delivery system. Yeah. It is not to the pain, but also liquid requirement. So now you see that, yeah, you can look at it. So how to then productizations? Then we actually start a company. So India has now the ecosystem of making a startup. So my student will show. So you have been able to see that how actually technology developed in the lab can go to the market and how to make this one. Okay, so with this, I like to end my talk because 2 o'clock almost, yeah, 2 to 5, so 5 minutes. So if you have any queries, doubt, you can ask or send me mail, or I can, and you can also find all my lectures in the websites. Uh, Especially if you just turn on the YouTube search, then you write microelectronics IIT Kharagpur, and there is a 1 hour documentary on my work made by Doordarshan. So you can actually watch that, where the details of all the process, whatever I have discussed here, and the machinery is required for that. So you will be getting that one, and so uh, don't. I was not able to give you the because time is short. Otherwise, I can give a uh, virtual uh, tour of the lab. Unfortunately, time is limited, but you can have a look of that. You are in YouTube. You find the microelectronics IIT Kharagpur Doordarshan DD. So you can click and then you can find this documentary where everything is very well cleared about what is sustainable technology and how the sensors being fabricated and what is the our plan. Actually, I have not even told you 2% or 10% of my work. There are many things are going on, so you can get a glimpses of that from that. So thank you all, and if you have any questions, you can ask me.
So all participant, if you are having any kind of query or question that you want to ask to our speaker, then feel free to ask.
I think all are hungry, so they are not ready to ask me any questions. Anyway, so you can always actually contact me in through my mail, uh, gkb@ece.iitkgp.ac.in, and also in the media. Uh, Renuka ji, you have to unmute yourself. So you are muted, basically. So if you have any questions, you can put on there, and also you just put the micro needles. You will get lot of attentions, reporting paper and all this. So you can find, and also you can download my paper appeared in Nature in last year uh, on the glassy carbon needles. So you just write glassy carbon needles nature, then you will find that paper. And you can also find all the papers, current and previous one, in the in my name. If you just Google me, okay, you just take my so you can get through that to get idea of this. Okay. So should I stop now? Yeah.
Yes, sir. Yes. Thank you, sir, for delivering such an informative speech. We are very enlightened with the work which you have done, uh, and we are honored to have you in this forum where we can explore the work which has been done in IIT Kharagpur for different, uh, different importance in terms of space agencies and medical field. So now there is a quiz link which is getting floated in the chat section. So I will request all the participants to please go and participate in that quiz. The link will be active for 15 minutes. So please try to attend the questions which are there. Those are very general and basic questions.
So can I say goodbye?
Thank you, sir.
Okay. Thank you.
Thank you, sir. Thank you.
So this one.
All the participants, please. Participant Sachin Singh is here from Gorakhpur. Sachin Singh, are you hear me? Sachin Singh,
Yes.
are you hear me?
Yes, sir.
Yes, sir. This type of things not happen in future.
Okay, sir. Thank you, sir. Yeah, I am doing quiz, sir. How
Yes,
much time for
quickly,
quiz?
you disturb whole the class for 2 to 3 minutes. You know, you are in market and you put your something phone is you unmute your phone, so that this type of things are not happen in future from any participants.